Okay, welcome to Robotics 1. In today's class, I'm gonna talk about something called as the forces on the robot. So actually, we are gonna talk about static forces on robot. Now, what do I mean by static forces? So the idea is typically the robot would have some forces and it will have some movements. So let me start with a very simple example that we have been talking about. Say we have a robot arm. And this is the same 2 degree of freedom robot that we studied again and again and again and again. And on this 2 degree of freedom robot, there is an external force F. So this is your end effector. And there is an external force. And this force could be maybe a gripper force, or robot is holding a paint can or something. Now, what we want to do is the only way this force can be compensated is by adding torques at the motors. So what I mean by that is if you have a motor here that is going to supply torque tau 1, there is going to be a motor here that is going to supply torque tau 2. And what we want to do is we want to find out the values of these torques tau 1 and tau 2 so that this load, external load, can be supported. Now, please note, this is a static problem. What it means is the robot is not moving. So what I'm going to do is I'm going to give you some joint values. So this angle is theta 1. This angle is theta 2. This angle is theta 1. I'm going to give you some lengths. This is L1. This length here is L2. And the idea is we want to find out the torques tau 1 and tau 2. If you were to look at the conceptual kinematic diagram, this conceptual kinematic diagram is going to look something like this. So it's going to look something like this. And think about it that at this end effector, you have some force. So there is some force, external force F. And we want to find out what is going to happen at the joint torques tau 1 and tau 2 so that these motors can support the external load. Now, since this is a static problem, we can use the conditions of static equilibrium. And those are summation of forces in x direction is equal to 0. Summation of forces in y direction is equal to 0. Summation of forces in z direction is equal to 0. Then the other condition is summation of moment about x is equal to 0. Summation of moments about y is equal to 0. Summation of moment about z is equal to 0. Now, I just want to extend this a little bit to give you an idea. So if you think about the Newton's laws, summation of forces is equal to mass times acceleration. In this particular case, the acceleration is 0. So velocities is equal to 0, acceleration is equal to 0. And the other equation, it's summation of torques is equal to I times alpha. In this case, alphas are 0, and these two equations, summation of force equation is represented like this. Summation of torque representation is represented like this. Now, how do we solve a problem like this? So if you want to look at the way the problem is specified, this is like a truss problem that we solve in mechanics of material. And all of you have seen the problem something like this. So you have a truss, and then you have some load F. And say what you want to do is you want to find out the loads in the link L1 and the load in the link L2. And assuming these are all hinge joints, what you do is you resolve the forces in X and Y direction. So for an example, if you were to sum the forces in the Y direction, sum of forces in Y direction, you would observe F is going down, and you have this force, which I'm going to call F2, is going to go up. This angle, if that is theta 1, so you would have plus F2 cosine theta 1 is equal to 0. And then you're going to have other force. If this is F1, you can, the summation of forces in X direction is equal to 0. That would lead to minus F1 plus F2 sine theta 1 is equal to 0. And you can, there are two equations and two unknowns. So you can solve these two unknown quantities. So you can find out what is the value of F1, and then you can find out what is the value of F2. So now the question here is, how do we solve this problem? So what I'm going to do is I'm going to start this problem with one link at a time. So we are going to start with link number 2. So this link number 2, let me draw the diagram for the link number 2. This is link number 2. And on this link number 2, there is this F. And on this F, I'm going to assume that this force F is going to make an angle alpha with respect to the link. So the force is making angle alpha with respect to this link. So this force F would have two components. It will have a component in X direction, which is F cosine alpha. It will have a component in Y direction, which is F sine alpha. And then what we are going to do is we are going to find out the moment given by this force about the hinge joint. So please note, this is the hinge joint denoted by M2. This is the hinge joint denoted by M1. And then there is nowhere else to apply the torque. So this is the torque. So tau 2. This angle is going to be theta 1 plus theta 2. This distance is L2 sine theta 1 plus theta 2. And this distance is L2 cosine theta 1 plus theta 2. So we will actually draw, first step is to draw the free body diagram. So the way, as the word says, free body diagram. So we are going to free the bodies. So let's try to look at what forces and what moments are applying. So if I free the body, I would understand, and I'm going to show it to you. This is L2. There is going to be Fx. There is going to be Fy. And here, there is going to be tau 2. Please note, there is no other force acting on this link. So what I'm going to do is I'm going to draw the reactions as soon as I free the joint. So please note, this M2 is a hinge joint. Initially, the value of forces at joint M2 are 0 because the forces are cancelled. But as soon as I free the joint, these internal forces, they come in the picture. These are called as the reaction forces. So you have Fx and Fy. So please note, these forces are internal forces. So, and what that means is, if you look at the other link, which is L1, this L1 is going to have exactly the same magnitude, but opposite direction forces shown in the red. And as these two links get combined, these blue forces and black forces, they cancel each other. So you have an action force and you have a reaction force, and they came into existence because we freed the joint. That's why we are drawing free body diagram. When those two links were combined together, when they were attached at the hinge, then at that time, these forces cancel each other out. So what I'm going to do is I'm going to write down the summation of moment about z-axis is equal to 0. And this equation can be written down. So focus on link number 2. This equation can be written down as tau 2. And this is positive because curl your fingers in the direction of tau 2. Tau 2 is positive. We are taking moments about M2. So taking moments at about M2. Tau 2 plus f of x L2 cosine theta 1 plus theta 2 and minus Fy L2 sine theta 1 plus theta 2. So you have these moments, and just for the sake of discussion, if you really want to consider summation of forces in the x direction and summation of forces in the y direction, you will notice that you are going to have, say, if you call this ry, if you call this rx, then you will just say fx is equal to rx and fy is equal to ry. Okay. Any questions at this point? Now, clearly at this point, what we can do is we need to move on, and then we need to go to link number 1. Now, what happens at link number 1? So at link number 1, you have ry, you have rx, and in addition to that, you have tau 1. And again, initially, this link number 1 was attached at the hinge, but I separated this link from the hinge. So this link is separated from the hinge. As soon as the link is separated from the hinge, you are going to have the hinge reaction. Again, they will come in the picture. And those hinge reactions are going to be something like this. And I'm going to call this, say, px and py. So now I have an equation I need to derive the equation for px, py, and this is my location m1. This is where the moment or the motor is. So what I'm going to do is I'm going to find out again for link number 1. So this is again for link 1. For link 1, I'm gonna write this equation down, which is tau 2. And one thing that I just want to mention, since there is tau 2, there will be a tau 1, a tau 2 here. So tau 2 over here. And these tau 2s, so please note, they are equal in magnitude, opposite in direction. So what I'm gonna do is, for link number 1, I'm gonna have tau 1 minus tau 2 plus, and again, let's look at the distances. So this angle is theta 1. So you are gonna have Rx L1 sine theta 1 minus Ry L1 cosine theta 1. But we know that Rx is equal to Fx and Ry is equal to Fy. So I can write this down as something like Fx L1 sine theta 1 minus Fy L1 cosine theta 1. So this is equation number 2. And I'm gonna say this is equation number 1. I'm gonna go, yeah, theta 1 and theta 2 values will be given to us. Our end goal is given the values. Okay, I was not clear perhaps. So given theta 1, theta 2, and F. Find tau 1 and tau 2. So sines and cosines, let me see, sine Rx theta 1 minus, so in for F1, so this is gonna be Ry, no, I think it should be L1 cosine theta 1 and This guy is L1 sine theta 1. Everything okay? Sine, cosine values? Any questions there? So I think this equation is okay. Now let me go to same thing. What I want to do is look at the equation for link 2. So you have an equation for link 2. This is the equation for link 2. So this is equation for link 2. This is the equation for link 1. Cosine describes the x direction. Yeah, that is correct. But we are looking at the moment given. So summation of moment about z is equal to 0. And that equation is applied at M1. So I'm looking at the moment. Okay. So now what I want to do is I want to find out what are the knowns and what are the unknowns. So here is how I would like to set this system up. So I'm going to write this equation something like this. Tau 1, tau 2 is equal to a matrix fx and fy. So I would like to write this equation down as something like this. And some of you may say it looks a little complicated because these equations, they seem to be coupled, and you would be correct that indeed these equations are coupled, but then I can actually simplify this equation a little bit. And the simplification can be written as, please note, from equation 1, you can represent tau 2 as maybe minus something like the quantity on the right hand side. So you get the quantity on the right hand side. And then from the second equation, you can substitute the value for tau 2 and then get the equation for tau 1. So I just want to clarify real quick here that how this kind of works. So you have tau 2 is equal to minus fx L2. So minus fx L2 cosine of theta 1 plus theta 2 plus fy L2 sine of theta 1 plus theta 2. Now you can use this equation for tau 2 and substitute in over here. The equation 1 is wrong. Okay, what did I make a mistake in equation 1? Let me see. F of x. Oh yeah. F of x L2. This should be sine. Okay, is it what you're saying? And f of x sine, yeah, and f of x cosine. Okay, all right. Yeah, so now we are on the same page. That's perfect. So f of x sine theta 1, and this becomes cosine theta 1. So with this, what I'm going to do is I'm going to make this substitution here, and then I would get the equation for tau 1 is equal to 0. minus f of x L2 sine theta 1 plus theta 2 plus Fy L2 cosine theta 1 plus theta 2. And let's not forget the remaining terms, which are like fx L1 cosine fx L1 sine theta 1 minus Fy L1 cosine theta 1. So now I have two equations wherein I have theta tau 2 and tau 1 that can go on to the left hand side. So if I want to take this on the left hand side, I'm just gonna say here tau 1, and I should be able to write this equation something like this: tau 1 tau 2 is equal to, and this is going to be a long expression, so you have to bear with me and make sure that I do not make mistakes. So tau 1 is equal to, I'm going to combine these fx values together. So this will look like minus L2 sine theta 1 plus theta 2. Then I have plus L1 sine theta 1. Then I have for Fy, which is L2 cosine theta 1 plus theta 2 minus L1 cosine theta 1. And please note, I have taken f of x and f of y outside. F1, let me see, fxl1 should be fxl1 should be negative. Let me see, fxl1. So curl your fingers in the direction of our
So fx1 sin theta 1, sir, from tau 1 minus tau 2, that equation, the equation 2. If you see fxl1 goes to that left side and it becomes negative, right?
Just bear with me for a second. Okay, fxl1. Okay. I see what you're saying. Okay. Yeah. So fx L1, yeah, correct. This becomes minus and this becomes plus. So this becomes minus, too many shortcuts, this becomes plus. Everything okay here? Anyone else? Okay, so moving on, now we have to express the same thing for the fx and fy, and this is going to be minus L2 sine theta 1 plus theta 2. This comes from the equation 2. And this next part is going to be cosine theta 1 plus theta 2 multiplied by L2. So this is what is how it looks. Any questions, concerns, ideas? Now, what I want to do here is I want to tell you something super duper interesting. Based on the analysis that we did so far, can someone tell me for the end effector? So I'm gonna say for end effector, there are two positions. There is P of X and there is P of Y. P of X is going to be L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Now Py is going to be something like L1 sine theta 1 plus L2 sine theta 1 plus theta 2. And what we did is we actually looked at the how the Jacobian got formed. And one thing I want you to note, this is very super duper important. Unfortunately, this concept is not discussed in statics, but please note, these are the sort of the displacements under force. And this concept I want you to think about for a minute. So if you think about it, we have our end effector and the force is acting on the end effector. We resolve this force something like maybe f of y and f of x. So what is this px and py? Px is nothing but the travel in the x direction, and py is nothing but the travel in y direction. Everyone understood this? This is super duper important because we have forces and we also found out the displacement on the end effector. And this displacement is expressed as the function, very important, this displacement is expressed as the function of theta 1 and theta 2. So what I'm going to do is I'm going to find out the Jacobian, or I'm going to find out the derivative. So let me write this derivative. And if you look at the way we did, so px dot py dot is equal to partial px divided by partial theta 1 partial px divided by partial theta 2 partial py divided by partial theta 1 partial py divided by partial theta 2. And we wrote this equation down something like theta 1 dot and theta 2 dot. Everyone with me so far? Any questions at this point? So what I'm going to do is I'm going to find out partial px divided by partial theta 1. So partial px divided by partial theta 1 is going to be minus L1 sine theta 1 dot plus L2 cosine, so I might as well write this as minus L2 sine theta 1 plus theta 2 multiplied by theta 1 dot. Since we have one more variable, this becomes minus L2 sine theta 1 plus theta 2 dot. Now, next thing is partial px divided by, so partial px divided by partial theta 2, partial px divided by partial theta 2. So I actually combine this together. So let me make it, let me do the exact same thing the way I have shown over here. Let me write this something like this. That way it will be easier to manipulate. And then let me do py dot over here. So that will make easier to manipulate. So rather than finding these individually, let me expand this and then I will put it in the same matrix form. So bear with me for a second. For py dot is going to look like L1 cosine theta 1 dot plus L2 cosine theta 1 plus theta 2 theta 1 dot plus L2 cosine theta 1 plus theta 2 dot. So what I did, I differentiated px and py. Now what I'm going to do is I'm going to write this equation px dot and py dot. And to be honest with you, this would be the only time I would solve this example all the way to the end by hand. Otherwise, from next class onwards, we will try to do the same thing using MATLAB. Because as you can see that the errors in signs are certainly possible. So now I'm going to write this equation down, something like this. So this is going to be minus L1 sine theta 1 minus L2 sine theta 1 plus theta 2 minus L2 sine theta 1 plus theta 2. Then I would have L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. And I will have L2 cosine theta 1 plus theta 2. And this would get written as theta 1 dot and theta 2 dot. Everyone okay with this? Now, what I want to do is, I want to show you an interesting comparison. Now, I want you, that's why I kind of shrunk this. So I want you to compare this equation, equation 4, and I want you to compare with this equation, which is equation 5. I want you to look at these two equations. All right. Yep. Somebody came with something transpose. So what has happened is this is the Jacobian. This is the Jacobian. So you can observe that the Jacobian gets transposed. So what is the key takeaway from here? If I take the Jacobian, I transpose it and multiply by f, I get tau. Now, this would be very, very important when we are going to solve the robot problem. So let me show you the actual derivation, why this works. So what I'm going to do is I'm going to find out something called as virtual work. what is the meaning of virtual work? So virtual work is nothing but I have these forces. These are the forces. And these are the displacements. The work is force multiplied by the delta displacement. So I'm going to call this delta D. So the virtual work is the forces multiplied by the delta displacements. So how would I write this equation down when I have multiple forces? So please understand what I need to do is I need to do something like this. F of x multiplied by delta x plus f of y multiplied by delta y, or in our convention f of x delta px plus f of y delta py. So this equation can be written in a notation form, a very simple notation form, f transpose times x. Now, next thing, what I want to do is I want to express the work done by the torques or the motors. So work done by motors or joints. And that work is nothing but tau 1 multiplied by delta theta 1 plus tau 2 multiplied by delta theta 2. So this is the torque, and this is the small displacement or change in the change in the angular displacement, change in angular displacement. So this equation can now be written as tau transpose multiplied by theta. So, and in case if you are wondering what is f is fx, fy. What is tau? Tau is tau 1, tau 2. And so I just have to be clear, x is equal to px, py, and basically tau. I'm gonna tau theta. Theta is going to be delta theta 1, delta theta 2. Okay, we don't need transpose. The thing what I'm trying to say is the mechanics works out. So why do we need transpose? I'll just okay, why do we need transpose here? Okay, so if you have a vector, so let me tell you why do we need transpose, and perhaps why do we need transpose. So the vector is say 1, 2, and if I want to multiply this by vector 3 times 4, please note this vector multiplication is not possible because 1 rows 2 column multiplied by 1 rows 2 column, this is not compatible. Not compatible. The only way this vector multiplication is possible if I were to write this is something like 1, 2, 3, 4. That leads to 1 multiplied by 3 plus 2 multiplied by 4, and that gives me a scalar number which is 3 plus 8, which is 11. That's why we need, you cannot just do a vector multiplication the way it is done. So for the dot product, this is one vector. So this is vector 1. This is vector 2. So you need to do the transpose. Eric, did you understand? Okay, so yeah, hold on. We will get there in just a second. We'll get there in just a second. So what I want to do is I want to write this equation uh, something like this. So start with virtual work. Start with work done by force. Work done by force is F transpose delta X. Do you agree with me? Then the next thing is work done by torque or the joint moment, which is tau transpose multiplied by delta theta. Since work and energy are similar, so work is equal to energy. So energy can neither be created or nor be destroyed. So basically, work done by the force should be equal to the work done by the torques. So this would be written as Ft. And what is delta X? So this equation, I want to show you here. This is delta X is equal to the Jacobian, and this guy is delta theta. So what I'm going to do is I'm going to write this equation delta X as J multiplied by delta theta. That gets equal to tau transpose multiplied by delta theta. And what's going to happen is I'm going to do a mathematical a matrix jugglery. And this matrix jugglery would actually be something like, I'm going to combine these two, since because there is delta theta here, there is delta theta here. So this can be written as F transpose J, and I'm going to take the transpose of the whole thing is equal to tau transpose transpose. So if you have a vector, you transpose this and transpose it back, then what you do is you get the vector itself. So for an example, if you start with 1 2, you transpose it, it becomes 1 2, you transpose it, you land up with 1 2. So this is transpose. This is transpose. So what happens is now you have F transpose J transpose is equal to tau. And I just want to give you this matrix identity. If you have AB, a matrix product where A is a matrix, B is a matrix, when you transpose the matrix product, the answer is B transpose A transpose. So think about it. If you take the transpose of this product, it's going to be J transpose F is equal to tau. Now, then the question is, how is this equation related to what we have over there? And at this point, I want you to look at this equation. Tau is equal to J transpose F. And believe it or not, this is equation 4. Are you with me so far? Any questions here? So Eric, that is the reason why we need transpose. Does that answer your question? So if you look at the equation that we have derived here, J transpose F Now, some of you may ask me, all this is great, but what is the advantage of solving using this technique? So many a times your robots, they move slowly. So robots are slow moving. So the robots that are slow moving, and what that means, they have some sort of quasi-static motion. So the robot arm goes from theta is equal to 0 to theta is equal to 2, waits there for some time, some operations take place, then it goes from theta 2 to theta 3, it waits there, some operations take place, then goes from theta 3 to theta 4, etc., etc., etc. So when the robot is slow moving or stationary, the Jacobian that we calculated using the homogeneous transformation and the velocity analysis can be directly used to find out the joint torques. Because understand, you don't want robot to run under gravity. So if the robot goes from point A to point B, you want that robot to stay at point B. You don't want that robot to drop down. So you can estimate the amount of torque that is needed to hold the robot at that particular point. That's why if you have a Jacobian, you can actually use that to estimate the potential torques that you need to go from point A to point B. Now, when we do the dynamic analysis, so please understand what is happening here. And I will go back for a second with, so when we are looking at the dynamic analysis, the accelerations, which are shown over here, and angular accelerations, which are shown over here, they cannot be ignored. So you will have some non-zero accelerations, linear accelerations of angular accelerations. So what it means is, in worst possible scenario, the inertial effects are going to require more torques. So inertia of the robot will require you to apply more torques. So in that case, these torques, tau 1 and tau 2 that we have found out would be increased by some slight amount. And that is the reason why sometimes the Jacobians are used to estimate the torques as the robot goes from point 1 to point 2 before the robot starts moving, because we want to make sure that the motors have the capacity to support the torques. Okay, so this analysis is super duper important. You can, and as you can see clearly, solving a problem in 3 dimension is a very complicated task. However, so let me pose this problem. So if I give you a robot, something like this. So this is the kinematic diagram. I'm going to show you a kinematic diagram. And maybe you have one more joint. And then here you have maybe a prismatic joint. Maybe you have a prismatic joint. Something like this. Now, with the technique that we talked about, and if this is the joint angle theta 1, if this is the joint angle theta 2, and maybe this is the distance d, I'm going to call this d3. And now I give you a force. So I give you a force which is something like this. And this force is also in 3 dimensions. What I mean by that is you're going to have a component fx, you're going to have a component fy, and maybe you will have a component fz. So now what I want to do is I want to find out the joint torques. This is very important. I want to find out the values of tau 1. I want to find out the values of tau 2, and perhaps I want to find out the joint force, which is F3. Rather than setting the three-dimensional kinematics equations, finding out force summation of forces at each joint is equal to 0 in 3 dimensions, you can directly go for this. You will say my Jacobian Px, Py, and Pz dot, Px dot, Py dot, and Pz dot is equal to the Jacobian multiplied by theta 1 dot, theta 2 dot, theta 3 dot. So you got this Jacobian. So obtained from a homogeneous transformation 0H3 and then differentiating Px, Py, and Pz. You can D3 dot, that's correct. So D3 dot, D3 dot, D3. So what you can do is basically you can grab this Jacobian, and now you want to find tau 1, tau 2, and F3. You can grab this Jacobian, do this transpose, and multiply this by Fx, Fy, Fz, and you got the joint torques without writing the equations for summation of forces is equal to 0, summation of moment is equal to 0 for all 3 joints. Okay, everyone understood why this analysis is super duper important? So I just want to say that this is super important. So that allows you to solve 3-dimensional static problem in a jiffy. And they also give you the estimates on the joint forces that you need to obtain that particular end effector position. Any questions here? Everyone understood this? So what I'm going to do is, yeah, I know this is little maybe too much to absorb in one lesson, but I just differentiation. So diff means the differentiation. Where did I write this down? Okay, so this is the differentiation. Okay, the just last part, right? So the idea here is, so we are very comfortable with, doing the forward kinematics. What happens in forward kinematics? In forward kinematics, finally we get 0H3 in this particular case. In 0H3, you are going to have 0R3, and you are going to have Px, Py, Pz. You're going to have 1, and you're going to have 0 here. Now, what you will do with that is you will obtain Px, Py, Pz, equations for Px, Py, Pz. And with this, you can find out the Jacobian. So Jacobian would look like, for an example, Px is going to be function of theta 1, theta 2, and d3. Py is going to be function of theta 1, theta 2, d3, and Pg is going to be function of theta 1, theta 2, and d3. Everyone understood this? Px is going to be the function of theta 1, theta 2, d3. Py is going to be the function of theta 1, theta 2, d3. And Pz is going to be the function of theta 1, theta 2, and d3. So Px, Py, Pz, they are dependent variable, and theta 1, theta 2, theta 3 are independent variable. So what I'm saying is at this stage, you can find out the derivative of Px dot, derivative of Px dot, derivative of Py dot, and derivative of Pz dot. And derivative of Px dot, derivative of Py dot, and derivative of Pz dot is gonna look like something like this. And I'm gonna express this as partial f1 by partial theta 1 dot plus partial f1 by partial theta 2 dot plus partial f1 by partial d3 dot. Yes, so f1 is this function, right? Just say this is the function. Yeah. So that is f for functions. Same thing is going to be partial f2 partial theta 1 dot plus partial f2 partial theta 2 dot plus partial f2 partial d3 dot. Same thing is going to happen here. Partial f3 theta 1 dot plus partial f3 theta 2 dot plus partial f3 partial d3 dot. Now this equation can be written as px dot py dot pz dot. And please understand that we are not going to do these calculations by hand. So we are going to use MATLAB. But I want you to understand what is happening mathematically. So theta 1, partial f1 theta 2, partial f1 theta d3. This is becoming partial f2 theta 1, partial f2 theta 2, partial f2 partial d3, last but not least partial f3 theta 1, partial f3 theta 2, partial f3 partial d3. And then you're going to have theta 1 dot, theta 2 dot, and d3 dot. So this guy is the Jacobian. And once this Jacobian is calculated, you can find out torque 1, torque 2, and F3. F3 is the joint force or the force given by that linear actuator. Tau 1 is the torque of the first motor, torque motor 1. Tau 2 is torque motor 2. And F3 is force by joint 1 or joint 3, which is cylinder, is nothing but Jacobian transpose Fx, Fy, Fz. So this is how you can actually find out the joint forces and moments. Does that answer your question? Kanji? Anyone else have any question? So, and again, my suggestion to you would be review this material. What is your question, Vishnu? If we have an end effector, yeah, so the question can be posed something like this. You have a mass that is located here. Yeah, I would post the notebook on Canvas, absolutely. If you have mass, so clearly there is no fx, there is no fy, there is only fz, which is m times g. And then what you do is just substitute everything else is equal to 0, and you can find out the forces that you need to support that mass. Yes, this notebook is saved. One note didn't crash, so I would actually post this notebook on Canvas. Now, this is very, very important. Even shrink and the motor weights will be added. Or yes. So the way that is done is something called as compensation. So usually the motors are supplying torques to support the static load. And I give you an example. So an example is something like this. Just think about this robot, a single arm robot. And this robot has some mass m. So clearly you have m times g, which is m is the mass of the robot. You have some m times g force acting that is going to give you, say, if this distance is L by 2, then you're going to have, if you're going to have mg L by 2 cosine of theta. So this is theta. This torque is going to get applied if the robot is at its position shown. So the idea is, whatever motor you have, the motor that you have over here is supplying the torque. Motor is supplying the torque, tau, that is compensating the torque or the moment given by gravity, so that this robot arm stays in this equilibrium position. So that is what the motors are supposed to do. So there is something called as the static or the holding torque. So tau, and think about it as holding torque. And now let's make this problem even more complicated. This robot arm is supposed to carry some weight, which is capital M. So clearly now the holding torque is going to increase something like M G L cosine theta. So that's why you need the motor that can compensate for this holding torque. But this technique, this is called as the method of virtual work. And this is very important, method of virtual work. This method of virtual work allows me to calculate joint torques and joint forces. And these forces can be function of time. And when we are going to look at the equations of motion, so please understand all this can be used. F is equal to m times a, and t is equal to I times alpha. The method of virtual work is used to find out these guys on the left hand side. So this, what we discuss in today's class, is going to be super duper important, because we are going to use this to find out the forces on the robot. So I'm gonna stop here, but I'm gonna quickly give you a rundown of what we did. So in today's class, we looked at something called as the method of virtual work, wherein we have some end effector forces, or the forces that are acting on the end effector. And then we want to resolve those forces in each joint. We actually used the conditions of static equilibrium and solved the two link robot problem. And then we found out that indeed, if we were to take the transpose of the Jacobian, we don't have to do any more resolution of forces. We don't have to do anything related to equations of static equilibrium. We can directly use the Jacobian that we know, take the transpose, multiply by the forces, and boom, we got the joint torques and joint moments. Yes, this is the method to go. This is the workhorse that is used to solve three-dimensional force problems. I don't know, probably you did solve three-dimensional resolve three-dimensional forces in statics and dynamics, but that was not fun. Do you agree with me? So but with method of virtual work, everything becomes super simple. And that's why I'm a strong proponent of teaching method of virtual work in statics and dynamics. And I use that exclusively when I taught statics and dynamics. But unfortunately, this happens to be the last chapter in statics and dynamics and does not get enough attention that it should ideally get, because method of virtual work will allow you to solve forces, resolve forces, find reactions in 3 and in multiple dimensions. So even the equations of static equilibrium may or may not exist when your coordinate system has 7, 8, 9, 10, 11, 12 complex coordinates. Method of virtual work always works. With that, I am going to stop here. So I'm going to stop recording.